So you are welcome. We want to discuss introduction to inferential statistics today, but our last discussion, the last part of what we did on probability and normal distribution, I think this is the last slide. You remember that we were not able to talk about the last issue on the slide because we were tired. Do you want to listen? So it's that area. Who is drawing on this thing now? Who is drawing on the, please behave yourself. Somebody is drawing something. I catch you. Somebody is drawing a racing. I don't know if I can erase it now. Is that person that can erase it? I think. Well, let me stop sharing. Maybe that will clear it. Let me reshare. Yes. Now remember, I asked you the question. Let's quickly look at this slide. No, you remember I told you that for continuous probability distribution, which normal distribution is one of them, you cannot know the probability of a given value, but you can know the probability of a range of value. You can say you cannot say what is the probability that somebody has blood sugar of 60, but you can say what is the probability that somebody has blood sugar of less than 60 or greater than 60 or between 60 and 70 or whatever. So a range of value, either between something and something or above something or lower than, so those are the things, those are the only things you can know about continuous probability distribution. So I now ask you, I think we asked that question. What was please you respond though. Somebody answer correctly that day. I said, what was the probability that somebody, because we have already cleared the issue that the mean blood pressure, I said that this graph you are seeing is both in normal distribution and standard normal distribution of systolic blood pressure. You see, the upper one is the normal distribution. The lower one is a standard normal distribution, which have been converted to z-score. And I now ask you, what was the mean blood pressure? Somebody says 100. What is the standard deviation? Somebody says 16. So we have cleared that. But the question where we were stuck, or whatever was, I asked what was the probability that somebody had blood pressure of 100. What is the answer? The probability that somebody has blood pressure of 100. What is the answer?
0.
0. Thank you, Amanda. Is 0. Okay. What is the probability that somebody has blood pressure greater than 100?
50%.
50%. Thank you. Okay. What is the probability that somebody has blood pressure greater than 116? 1. What is the probability that somebody has blood pressure greater than 116?
1.
15?
How can it be 16? Because how do you get 16? Anyway.
25%. 25%.
Okay, if you can explain how you calculate it. Who says 60? Who says 20? How do you calculate it? Is it logic now? Nobody.
25%.
How is it 25%? In those of you are not confident. Somebody that says 16, why is it 16? 16 is, why is it 16? 16 is actually correct, but why is it 16? Because the 16 is possibly because of 116. It's not that 16 standard deviation. It's not that the 16 that is the standard deviation. But it's 16%. But how is this 16%? If you cannot explain that, that you don't know it. It's just gambling.
Excuse me, sir.
Okay.
Is
Yes,
it
go.
the difference between 131 and 116?
The difference between
131 and 116.
it cannot be now. That's what you see. That's why you are not getting the logic. You are not getting the logic. Now, maybe we'll come back to the. Okay, we said that when we said that, what is the. Okay. When we said that, we said that 68 point. The area under the graph is 100%. So we now say in between -1 standard deviation and +1 standard deviation, 68.27%, which we can approximate 68%, have the value in between the two values. So what is telling us is that in this graph now, between 68% of the people have value between 84 and 116. If I ask you what is the probability that you have blood pressure, the blood pressure has blood pressure between 84 and 116, you can say 68%, because that is the area under that graph. If I say between 69 and 131, what is the percentage?
95.
95%. That's the probability. So when I say greater than 100 is 50%, because 100 is the mean here, is the half, 50%. So half of the whole is 50. Less than 100 is 50%. And I say greater than 116. If you know that between 68 and 116 is 68%, and you know that greater than 100 is 50%. So logic, you should be able to know that between greater than 116 is 16%. So nobody has gotten it. See now. Who can say it? Who can explain why? That between greater than the probability that somebody have blood pressure greater than 116 is 16%, is 0.16. Who can explain it? Nobody. You know that if you want to know, anything above greater than 100 here, the area is 50%. Now, in between 100 and 116 is half of between 84 and 116. Between 84 and 116, we say is 68%. So half of it will be what? 34%. That shows that between 100, somebody have blood pressure between 100 and 116 will be 34%. So if that's 34%, and you know that anything greater than 100 is 50%. When you remove 34 from 50, what would give you? Will it give you 60%? Oh, what was between greater than 131? Blood pressure greater than 131. What is the answer? Somebody have blood pressure greater than 131. Nobody.
If I 4 point.
Amanda, what's it?
I don't know. I'm just thinking maybe 4.45, 4.5.
How can it be 4.5? Because you know that between 69 and 131, somebody says 95%. Is that not so?
Okay, 16 divided by.
So it will be 2.5.
Simple, 2.5%. Greater than 131, 2.5%. Less than 69, 2.5%.
2.5. Both of them are 5.
Yes, it's the same thing. Less than 100 is 50%. Greater than 100 is 50%, because 100 is the middle. So the probability that someone have blood pressure between 100 and 116 is 34%. Between 84 and 100 is 34%, because we know that between 84 and 116 is 68%. Half of it is between 84 and 100, and between 100 and 116. And that's what we have already said. Greater than 116 is 16%. Less than 84 is 60%. Okay, what are the probability that somebody have blood pressure between 69 and 84? Between 69 and 84? Nobody. Nobody is disturbing the class. Nobody. So between 69 and 84, you know that anything less than 84 now is 60%. We have already know that. Because anything, when we say greater than 116 is 60%, the same thing. Less than 84 is 60%. If we know that less than 69 is 2.5%, between 69 and 84, we remain 30.5%. Well, you logic. Now, we now said that this is the last part of it that day was that, okay, we are talking about normal distribution, but we now have skew distribution now. You now have this negatively skew, positively skew. The left skew, which is negative skewness, is when you have an outlier. That outlier is extremely smaller than the rest. When you have outlier extreme value that small, extremely small, it will jack down the mean. So that the mean will be small. So that is why you now see if you are moving, we are moving from the origin of the graph, where from the zero you are moving, you see that mean first because it's smaller, median before mode. But if you have an outlier that is a big one, big outlier, which is positive outlier, it will be skewed to the right. In that situation, mean comes first. In mean mode comes first. So mean will be the largest, highest. Can you see? Mean will be the highest. So that's what I just wanted to explain. The other one, I think I've talked about it before. Under descriptive statistics, we talk about kurtosis and this kurtosis of skewness. We talk about it. Gbemisola, are you asking a question or you are disturbing the class? Okay, so let me just stop that because the question. So Amanda, you are laughing at what? So let's just talk about today's business. All those one is not today's business. So let's talk about today's business. Yes, we want to quickly look at inferential statistics. We talked before that the statistic as a subject is divided into two, descriptive and inferential statistics. And we have discussed descriptive statistics when we talk about descriptive statistics, and we also said that the link between descriptive and inferential is the probability. So after we discuss descriptive statistics, we also discuss probability. We just finished discussing probability. Now, let's talk about, have a glimpse at inferential statistics. Why I call this introduction is that after we finish this lecture, we now begin to talk about specific inferential statistics like chi-square, t-test, all those stuff. So before you can understand that concept, before you can even understand it and interpret it, you must understand what we want to discuss today. There are three kinds of lies: lies, damn lies, and statistics. That's what Disraeli said. Disraeli, the former UK Prime Minister, have this to say. So people can tell lie with statistics. And it's because when you don't know your descriptive inferential statistics very well, you tell lie. So let's talk about what is the meaning of inference, because that's where the inferential comes from. Inference. Inference is a generalization you make about a large group of or population from the study of a sample of that population. You study population. For example, now somebody want to know something about market women in Abuja. There are plenty. And you took sample, maybe 800 people or 600. You conclude, now say, 20% of the market women in Abuja are obese. So that is generalization, because the market women in Abuja, there are plenty. If they are not more than a million, they are not up to million. Now, you just take 800, not even up to 1,000. You take took sample. You now say 80%. We say work done among market women. Not in some people will say in North Central. Some people will say Northern Nigeria. Even some people quoting from outside Nigeria say in Nigeria, the work done among market women in Nigeria, find out that 20% of them are obese. That's generalization. It's an inference. So generalization you make about a population or a group by just study a sample, that's different. And I don't know, okay, I don't think I've discussed the difference between inductive and deductive with you. So there are two types of this inference: inductive inference and deductive inference. In inductive inference, if you go from specific to general, you make your observation, you design a pattern, you make a generalization. That's inductive inference. But in deductive inference, you hold a theory. Based on it, we make a prediction of its consequence. We predict what the observation will be in the case of hypothesis testing. So, when you do hypothesis testing, actually in hypothesis, the conclusion about your study is deductive inference. Any general, if your work, it's not all the study that test hypothesis, get to know. In fact, most of the MPA study you'll be doing, you are not going to be testing hypothesis. Only few. Most of that is only few among you that are good enough or that have got to do something, something different, that we want to do something that will make you to test hypothesis. Then by that time, the generalization you make in your study will be called deductive inference. But for most of you, it will be a descriptive study, and the generalization you make is deductive. Let me just, there's a lecture here I actually give it. There is no general, it's just logic or scientific reason. I actually talk about this, the way induction and deduction, the way people, scientists reason. Now, let me just give you an example. If somebody want to do a study, pattern of driving in Abuja, you just want to know pattern of driving in Abuja. Just give you 1 minute. So I'm back. Now, pattern of driving in Abuja. In this pattern of driving, you didn't have anything in mind that, before and say, women are more likely to have accidents than men. This one, the people that have license are more likely to have, are less likely to have accidents than people that don't have license. Underage person are more likely to have accidents. You don't have anything in mind like that. You just a pattern of driving. So that type of study is what we call descriptive study. You just want to know, but of course, you do your literature review, you know many things that may be said about driving. You want to include questions about that. You say, did you go to driving school? Do you have driving license? How old are you? When did you start driving? You want to know the sex of the person, many things. Have you had accident before? Have you hit somebody before that hit you? Many you ask questions around driving. You obey traffic light? Do you understand traffic light? All those stuff. You may say, have you gone for training before? You ask many questions about driving. But by the time you ask your question and you do your analysis, you may then begin to do what we call cross-tabulation, where you say, you are looking at some factors. It's like there are women are more likely to hit somebody than men. We say the underage are more likely to have accident. The person that have license are less likely to hit somebody than the person. In that situation, you are creating theory. You are trying to link it. Oh, people that don't have license, they will have, they are likely to hit somebody. So you are trying to create hypothesis or theory, from your work. But the issue, the generalization you are making there is what we call inductive inference. Inductive inference, that type of generalization. Because from the day one, you don't have anything in mind that there's an association between two ways. You just study something. So whatever you got from it, you will now begin to see some pattern. But some of the pattern you brought out in your result, if you publish it, some people may say that, some people have said that a work has been done before. They said that people that didn't go to driving school are more likely to have accident in this Abuja. And that's actually true. You now want to prove it. If you now want to prove it, then you may have an hypothesis that licensure, there's an association between having license and having accident. To people that you may not say, your research question is, the people that have license, that don't have license, are they more likely to have accident than people that have license? In that situation now, it's an hypothesis because you are linking accident. You are already creating a theory, a hypothesis between two variables, that there's a relationship, there's an association between them from the beginning. That is the reason you even want to do the study. So at the end of the day, it may be true, it may not be true. But the issue there, that conclusion you're going to make, the generalization you're going to make about the population, based on that your study is called deductive, because from the beginning, you start with hypothesis testing. I think it's very clear. If you don't understand, let me know. It's very clear. So we are talking about inference now, which is generalization you make about population from the sample. Let's look at sampling distribution. The next concept you want to look at, sampling distribution. What is sampling distribution? This issue of distribution, we came across it when we were talking about descriptive statistics. When we came to probability, we talk about distribution, because we talk about probability distribution also. When we're talking about descriptive statistics, we talk about 4 types of distribution: frequency, relative frequency, cumulative frequency, cumulative relative frequency. When it comes to probability, we talk about continuous probability distribution and discrete probability distribution. That's when we talk about probability distribution. Now here we talk about sampling distribution. It is in logic. Why for the distribution we are talking about, we say, when we first talk about distribution, when we talk about frequency distribution, we say distribution is pattern of occurrence of value of a variable in a data set. But here is pattern of occurrence of sample statistics obtained from samples repeatedly drawn from one or more populations. No, we have already said that in descriptive statistics, when we summarize what we get in our sample, the summary is called statistic. If you say the mean age is 34, that mean age is statistic. But the mean age in the population is parameter. If you say the percentage of women or female in the population is 52, from your sample you've taken, when you took sample, you count how many male, how many female. You now say, oh, percentage of female is 52. That is statistic. The real percentage of female in the whole population is parameter. So when you saw, anytime you take sample, you summarize. Whatever you calculate, either sensitivity, specificity, mean, mode, median, standard deviation, anything, percentage, either rate, proportion, ratio, they are all statistics if you calculate them from sample. But the corresponding value in the population is parameter. So when we say pattern of occurrence of sample statistic, you should know that in that situation, they have summarized a sample and come with. So here, statistic now has plural here. It's not talking of the subject. It's talking of the summary of sample. But because this one is a plural form, sample statistic, when you have many statistics, You calculate it. That's why we put S here. So pattern of occurrence of sample statistics obtained from sample repeatedly drawn. What they are not telling you is that you take sample, you calculate it, you summarize. You take the sample many a time, you summarize the same thing. You know you are going to have different value. So what is the pattern of occurrence of it? That is sampling distribution. So if, let's say, for example, now you measure the weight of people in the population, you take a sample in the population, maybe sample of 50 people, 100 people, 200 people, you measure their weight, you calculate the mean. That is you are calculating. So the way the value, the way the weight vary among them, that is distribution of the weight. The weight vary, the value vary among them. How many weigh 67? How many weigh 50? How many weigh among them? That is distribution. We are talking about that one. But here, that is the distribution on a simple way. But the sample, the sampling distribution is when you now take sample many a time. For each of the sample, you summarize what is the mean weight. You know, so if you do it 70 times, you have 70 values. So it will vary also. Some of them will be the same, some may not be the same. You may have some of them, we have the 68 kg, 68 kg, 68, 70 kg, 72. The mean, the value you calculate for each of the sample. So when you have the pattern of occurrence of that value is the sampling distribution. I think you should be able to conceptualize it now. So for you to conceptualize it further, so from what we have just explained now, when you do that, you go to have what we call sampling variation. You can see now, sampling variation here means that if you take sample many a time, you calculate the statistic. You see that it will not give you the same. Some may be the same, but it's not possible for when you measure many a time, you take many a time, what you calculate will be the same. If it is mean you are calculating, or if the percentage you are calculating, whatever you are calculating as a summary statistic, when you take sample many times for the same thing, and you now say that you cannot get the same thing, it will vary. That's why there's sampling variation. Now, the issue of standard error now is when you now take sample many times, and you now, all of them, they have different values. Some may be the same, whatever. You now say, okay, let's calculate the average. You calculate the average. That average you have calculated of all those statistics, it is believed it is equal to the parameter. That is, you are trying to, okay, imagine you take sample of adult in Abuja about 50 times. You calculate mean weight, you measure their weight, you calculate 50 times, maybe for each of them, maybe about 150 or 200 of them, and then whatever your sample size is, maybe you take it 50 times, calculate their mean. That's why you have 50 means. You now say, let me calculate the mean of the mean, average of the mean. That average, people believe that it is equal to the real mean in the population. You know, for you to get the parameter, you have to take the weight of everybody, every element in the population, which most times is not possible most times. So, but if you now take many sample many times and now calculate the average, it is believed it should be close or should be equal to the real mean, as if it should get if you are taking everybody and calculate the mean. So the mean of the sampling distribution is believed to be equal to the parameter. Now, since you can calculate the mean, and you know that each of them can vary from the mean, you can calculate the standard deviation from the mean of each of those mean from their own mean. When you calculate the standard deviation, that standard deviation of the sampling distribution is called standard error. Standard deviation of the sampling distribution is called standard error. And it is believed is equal to the population standard deviation. Can you see that? We say that the mean of the sampling distribution is believed to be equal to the parameter, while the population, the standard deviation of that sampling distribution is equal to it's called standard error, equal to the standard deviation in the population.
Standard deviation of the what again? Is the standard error.
The standard deviation of sampling distribution is called standard error. Standard deviation of sampling distribution is called standard error. And it is believed to be equal to the standard deviation in the population. Can you see now? That is why many people now oversimplify it. They now say standard deviation is population. And they say standard error is population standard deviation. No, it's just a proxy. The standard error is standard deviation of sampling distribution. There is a proxy that is something if you believe that to be equal to represent the population standard deviation. So you cannot just say blindly and say standard error is population standard deviation. No, but it's a proxy to it. Does it make sense now? Do you have any clarification? So now, this is what somebody now, just an illustration, what I just illustrated, I just said now. Let's imagine we have a population, this big, this cycle now, space population. Let's say what you are seeing inside the household, number of children in the household, in each of the household, the population, number of children. And from this big population, if let's say the mean average number of children in that population is 3, can you see mu in the population? Mu is 3. And somebody now took sample of 4 family household, 4 family, many times, 9 times. Can you see now 9 times from that same population? And now calculate the average number of children in the household. You will see, you have 3, 2, 4, 3, 1, 4, 3, 5, 2. If you look at it now, it tries to represent in a graph. How many has 1? If you are following, how many is 1 out of the 9? How many has the average number 1? Respond, unmute and respond. I want you to.
1.
1. Can you see the graph now? Under 1, can see the height of it. The frequency is 1. How many has 2? Mean of 2?
2.
2. Thank you. Can you see now? Under the 2 in the graph now, the frequency is 2. How many has 3?
3.
3. Can you see under the 3 now, the frequency is 3. How many has 4?
2.
2 also.
2.
How many is 5? How many is 5?
1.
So what this one just demonstrates, that's the typical the way it happens, especially if that attribute follow normal distribution. In the way it happens in the population, you will see that the average, if you look, is 3. If you had all those average together, all those 9 averages, 3, 2, 4, 1, 3, 3, 4, 5, 2, divide by 9, it gives you 3. So the average of it is 3, and which is equal to the mean in the population. That is the mean of, because all the bias are seeing mean here, they are statistics now. Because they are calculated from the sample. When you now calculate the means of those 9 statistics, the mean gives you 3, which is equal to the parameter mu. And if you now calculate the standard deviation, that standard deviation is 1.22. That is standard error, because standard error of all standard deviation of all these statistics is standard error. And it's the belief that it will be equal to the standard deviation in the population. If the mu is 3, the standard deviation also will be 3. Does it make sense? Can you see now? That's a glimpse to realm of inferential. Because inferential study, you just want to know what is happening in the population because you don't have access to the population. You have access to the sample. After you have already done your descriptive statistics, because you have the sample to do anything about descriptive statistics. But use from the value you get from the statistic, how do you have an idea of what is actually the real value in the population? That's the essence of inferential statistics. Can you see the starting point now? Now, let's move further. Before, okay, let me explain. This standard error now, which is the population standard deviation, which is a proxy to population standard deviation. Nobody to be sincere with you. Bro, in those days, they do that. And the way they do is not see the way it was through gambling. You know, statistics, people that started that study statistics early, they were actually going to Monte Carlo, you know, they go to where they do casino, gamble to collect data. Because that's when nobody, you don't need to get permission, say that, oh, go and gamble. People gamble on their own. Unlike now, if you want to collect data, you want to ask somebody a question now, it may not give you permission. But you go there to gamble on their own. So data are available like water. You go there to get data to study statistics in those days. Now, there's nobody to be sincere with you when we say you want to calculate standard error. We are talking of sampling distribution and begin to take sample 100 times, 50 times. See, I'm calculating standard error for Abuja for weight. Now begin to take sample of 800 people 50 times, 100 times, 200 times. Nobody does that again. What people do, intelligent people over the years now discover that if you calculate the standard deviation once, that is, you take your sample, for example, sample, you calculate the mean and standard deviation. You now divide it by square root of sample size to give you the standard error. And you see now, standard deviation over square root of sample size is called to the standard error. Standard error is standard deviation over square root of. What it means is that your standard error from this equation you are seeing, your standard error will be, okay, well, I want to let me put the word. Let me ask you, if you increase sample size, what will happen to standard error?
Reduce.
It will what?
Reduce.
Reduce.
It will reduce, yes, it will reduce. But if you increase it, it will reduce. But if you reduce sample size, your standard error will increase. Is that also? But the relationship now, because when you reduce your denominator, the what you are calculating will increase. But when you increase your denominator, the value, your answer will reduce. Now it will reduce. Is that also? So sample size, the higher the sample size, the smaller the standard error. So let me now tell you, what is the essence of this standard error? We say is the population standard deviation. What is the essence? If the standard error is high, it may mean two things. It may mean that your attribute, the attribute you are measuring, if your standard error is high, it may mean the attribute vary a lot in the population. For example, now, we have been talking about weight and height. We say weight vary more than height in the population. That is, weight differ among people than height. There are some things that differ. They differ among people. While some attributes, they are very close in value among people. So the attribute that differ a lot, that shows that their standard error is high. While the attribute that don't vary much among people, the value don't vary much, their standard error is low. Can you see now? So if the standard error is high, it may mean that that attribute, it differ a lot. Another thing that may be the reason is that your estimate, what you have calculated as your statistic, is far from the parameter. Does it make sense now? You know, we have already said that when you do your descriptive statistic and you are interested in the parameter, your descriptive statistic, what you get from your descriptive statistic is an estimate. If you calculate the mean weight for 800 people, representing about 5 million people, what you calculate is an estimate. You cannot be sure that it's the same value. If you have had every value together for the whole population calculate, it may not be the same. It will not even be the same. Not that it may not, it's not the same. So whatever you calculate your statistic is an estimate. So when your standard error is now high, it means that your estimate is far from the parameter. But when your standard error is small, it may mean that the attributes do not vary much in the population. It may also mean that what you have calculated as your estimate, as your statistic, is close to the real parameter. Does it make sense? That is the logic.
Sorry, sir.
Yes, go on.
So if the estimate is close to the parameter, would it make you more confident that your calculations are a true representative of the population?
Of course, that's what it means.
Okay.
And the only way you can get that clue is when your standard error is small. Because if your standard error is small, it means your estimate is close to the parameter. Is the standard error, the value of this standard error that give you the clue that your estimate, there's no other way for you to know if your estimate is close to the parameter unless through the value of standard error. Does it make sense now?
Yes, sir. Thank you.
You're welcome. Now, we have talked about standard error. Let's move to the next one I want to unpack about inferential statistics is central limit theorem. Central limit theorem. From what the picture I put in, you have a clue about what this thing is all about. You will see one graph here is skewed. It's skewed to the right. You see one is like a rectangle. That is not a normal distribution. This one is more like binomial distribution. You see the one that bar chart. You see the one skewed to the left. All of them, you cannot see those graphs follow. They are not normal distribution. They are pointing to normal. That what it means that all these you are seeing, underline them, under them, there are something about normal distribution under them. It's just like when you see people dress in different way, speaking different language or speaking English, doing many things, a class, different profession. But the issue is that all of us, we are all human beings. Okay, we are all human beings. When the sheep are down, people will behave the same way. Yeah. Now, this central limit theorem says that sampling distribution of certain statistics. No, we have already explained sampling distribution now, so you know what it means. Sampling distribution of certain statistics will approach normality as sample size increases regardless of the shape of the sampled population. When we talk about shape of the sample population, whether the thing is normally distributed or not, the sampling distribution of the statistics will approach normality. So there's something I need to still say about that sampling distribution we just talked about. You know, I use example of mean. That's just the simplest one for you to understand. When we say statistic, it doesn't only mean that statistic. You know that percentage is statistic because it's part of summarization of sample. You know, for categorical variable, we use percentage, which is proportion, or rate, or ratio. All of them are called ratio. The special form of ratio is the proportion, which we spell most of the time as percentage. And a special form of percentage or proportion is rate. That's how you summarize categorical variable. But for quantitative variable, numerical variable, you use mean, mode, median to summarize. Now, you also use standard deviation. All those things, measure of central tendency, measure of dispersion, measure of relative position, measure of distribution shape, all of them that are around quantitative variable. They are all statistics. So it's only that we just talk about the mean. So even the percentage is statistic. For example, now, let me just tell you, I think at the beginning of our discussion, I don't know, I told you something when we're talking about, we're discussing discrete statistics about classifying variable into numerical and categorical. Another name for numerical is a quantitative variable. Another name for categorical is qualitative variable. And I told you that it should not confuse you about when you say, because if you say quantitative variable, the data you get from it is quantitative data. If you say qualitative variable, the data you got from it is qualitative data. It may confuse when we are talking about quantitative and qualitative research. I told you. I say quantitative research. Any research you do, at the end of the day, you summarize with, you're going to use survey, question, all those questions, and you're going to ask different questions. Some of them are categorical, some of them are numerical variable you capture. You summarize them. Some, the numerical, mean, the standard deviation, the categorical, you use percentage. Whether mean or percentage, are they not number? They are all number. Whether it's a standard deviation, is it not number? When you say mode, is it not number? Median, is it not number? Sensitivity, number. Specificity, number. Think of all those range, number. Deviation, number. Variance, number. Standard deviation, number. Standard error, all this. All those, are they not number? They are all number. So, because that type of research is usually summarized with number, that's why I call it quantitative research. Whereas the other one that, when they do the research, they say they are doing focus group discussion, informant, and it be too much word. You'll be recording whatever. Some people will be talking nonsense. You'll be recording them. They say they are, some of them that you are asking them, they know what you want, they will be telling you, and you recorded them. At the end of the day, you now quote them that this is what they said. So the way you summarize it, in your report, you will not put number. You say most of the villagers, the community people say they prefer to have the to pay the to prefer that the care facility is close to their house. You will now quote them that this facility, if it's not close, if it's not close to our house, forget about it. We will not go there. No, you quote them, and summarize. There's nothing like number. That's what they call it, qualitative research. Can you see now? And sometimes also, when all these they are recording video, audio, and their transcription, they write those things. They say it's qualitative data. It's data. Everything is data. In the internet, anything is data. Even picture is data. No? Data. Anything that's no number, data. The one that is number is data. So they call those one qualitative data. Whereas those one that are those from quantitative research, call it quantitative data. Does it make sense now? So I'm just trying to let you know that. Now let's come back. So in the sampling distribution we discussed, you will see that even if it is percentage you are looking at, it's the same thing because it's number. So if we summarize, so what is the percentage of women in Abuja or in the Abuja market? No, it's not only women that go market, that go to, that do business. Though it may vary across region. In the West now, most of the time, it's the women that do business more. In the East, both men and women do business. In the North, even you discover men do business more than women. Can you see now? So let's say now in the market in Abuja, what is proportion of female that do business? You may say the percentage is 55% in the market. Percentage of women business owner in the market is 55%. That 55% is number. If you take sample, like the sampling distribution, you may take sample 100 times. You calculate, another one will give you 60%, another one will give you 30%, another will give you 25, 50%, 52%, 55%. You have different percentages, which you can calculate the average of it. And I say the average of this percentage is this. That will be the parameter. That will be the value of, okay, if let's say you are taking the whole population or the market, taking everybody into consideration, what will you get as the percentage? That average of the percentage you have gotten from different samples you are taking, that will be it. So it's not limited to mean. It's anything. Sample statistic, that is, any value you have calculated from your summarizing the value is what they are talking about in sampling distribution. So you can calculate the mean, which will be equal to the parameter. You can calculate the standard deviation of it, which is called standard error, which will be equal to the standard deviation of population. Can you see now? It's now quantifying everything. Even those things you think are not numerical, like sex, religion, ethnicity, color of the this thing, where you stay. No, all those things you think they are non-numerical, but somehow, as you are talking about this sampling, everything become quantifiable, and that is where the central limit theory is going. He is saying that whether anything is numerical or non-numerical, their statistics will then begin to follow normal distribution. Their sampling distribution. That is, if you take their sample, many times you calculate the summarization statistic, either for anything that follow normal distribution or anything that didn't even follow normal distribution before. Their statistics will follow normal distribution. Their sampling distribution. I think their sampling distribution will follow normal distribution, especially if you increase the sample size. If the sample you take, if the sample size increase, their statistics will follow normal distribution. Any question? Or we'll proceed? Central limit theorem. No question. This one is just putting graph to explain the same thing. Something that is not normal before, it changed to normal. So let's talk about hypothesis testing and confidence interval. Two categories of inferential method. So when we talk about inferential method, what method do we use to, do our inferential statistics? They actually have to 4 methods. The most popular are these. There's one called Bayesian statistics, Bayesian statistics, bias theory. We talk about that bias theory in the last 2 lectures when we talk about probability. When we talk about probability theory, we talk about the rules of probability, bias rule, rule 10. I talk about the Bayesian statistics. So that one, though it has been there for long, but some people are not bringing it. But people are not be using it for long. Popular one are hypothesis testing and confidence interval. There's another one called Monte Carlo method. Those one, they are It's not even being used anyway. They just exist in the realm of academics. Practically, it's not being used. Let's talk about hypothesis testing first. The meaning of hypothesis testing is a method of decision making. This decision relates to the choice between two competing, mutually exclusive statements regarding one or more population parameters. If you want to ask question, don't make noise. The competing statement of fact are referred to respectively as non and alternative hypothesis. Let me explain some of these things when you just be reading. When we talk about theory the other time, when we talk about inductive, deductive inference. When you say hypothesis itself is a statement of that of relationship or association between two phenomena, two variables. Example, there is an association or relationship between salt intake and hypertension or blood pressure. Let us say hypertension. Salt intake, blood pressure. That is, people, the amount of salt you take may determine your blood pressure. Association or relationship. You can use, because some people say the same, but sometimes when we get to regression, you now know that there's a slight difference between relationship and association. But let's just use it as the same thing. There's an association between salt intake and blood pressure. Or there's an association between socioeconomic status and teenage pregnancy. So when you talk about that association or association between level of education and employment status, education level and employment status, there's an association between sex and employment status, or sex and level of education. So you can think of two variables that are association. When you have a statement of association, that is an hypothesis, because it has not been tested. And the hypothesis now can be said in two ways. If I say there's an association, I can say there's a difference. You can use the word different. You may not use the word relationship or association, you can use the word different. Mean the same thing, but in a different way. If you say there's an association, you make mention of the two variables like I have done. You don't need to know which variable is exposure outcome. But if you have to use the word difference, you have to state. You cannot just say there's a difference between salt intake and blood pressure. Does it make sense? It doesn't make sense. If you have to use the word difference, you have to say, you have to know which one is exposure variable, which one is outcome variable. So whenever there's an association between two variables, there must be one that is causing the one, leading to the one. And the statistics itself does not tell you. It's you that will reason. Computer will not tell you. Software will not tell you. It's you that will know. For example, now, which one? The one that comes first will be exposure. The one that is as a result of the exposure will be the outcome. Okay, association between sex and employment status. Which one comes first? Which one is exposure? Which one is outcome? You can unmute and talk. Association between sex and employment status. Which one will come first? Which one will be the exposure? Which one will be outcome?
Maybe sex could be exposure.
Yes, you are right. Sex will be exposure because your sex may determine your employment status. It's not your employment status that will determine your sex. Okay, if you say there's an association between education and employment status. Which one will come first?
Education.
Education.
Education. Okay. If you say there's association between which one I want to put? Okay, we have already talked about it. Even association between age and level of education, which one will come first?
Age.
Age will come first. Yes, thank you. So association between blood pressure and salt intake, which one comes first?
Salt intake.
Salt intake. Thank you, salt intake. So you know, the one that comes first is the exposure. The one that will maybe, so something that is exposure may be, for example, now when you talk about sex and education, you say sex comes first. The education is outcome. But between education and employment status, education comes first. Education becomes exposure. Can you see now? So it depends on which variable this variable is relating with. It's just like as we are now. You meet somebody, it's your oga. You meet another person, it's your junior. So it depends. The person that's your oga is your oga with you. If that person meet another person, it becomes junior to that another person. So it depends. Now, after, okay, we have already established that now. Now, the same word, independent and dependent variable. Because the word exposure and outcome over the year was used by observational researchers, people that are involved in observational research over the years. Whereas the word independent and dependent variable used by people that carry out experimental design over the year. It's actually the same. Over the year now, they use it interchangeably. Like for example now, somebody that is carrying out experiment to see, okay, even though there are some experiments don't carry out with a human being. So for example now, you give education to some people, you didn't give education to some people, you now want to see their attitude or intake, maybe the effect of education on uptake of contraceptive by women of reproductive age. If you give education to some people, you don't give to some people, you now want later, you now measure their knowledge, their uptake of contraceptive. So if actually the education work, which one will have higher knowledge? By the time you measure their level of education in level of knowledge and uptake, which one? Which one? No answer. Nobody is answering. You have to unmute if you want to talk. Nobody in the class? Hello? I said that you give education, you want to know the knowledge of contraceptive among and uptake of contraceptive among women. And you now divided the women, went to one community, you give them education, you educate them about contraceptive. Another community, you didn't educate them. Later, they come back to measure the level of knowledge among the both communities. Which one will you think will have higher knowledge?
The educated
Ones
one.
that were educated.
The one you
The one
gave
we
education,
educated
not the educated one, the one you gave health education. Education is different from when you say somebody is educated, we are talking of formal education. But here, the one you give the health education, we have higher. So because you have influenced, because you want to measure knowledge, then you have done something to influence that knowledge in people before you measure it. That's why that type of research is called experimental research. So experimental research doesn't mean it has to be laboratory alone. To anything you do to influence what you are measuring. Maybe you want to know blood pressure how blood pressure is being controlled. You give drug to some people, you didn't give drug, or you give placebo, shock to some people, you give the active drug to another people. You measure their blood pressure. If actually the drug is working very well, the one that you give the real drug to, we will have better blood pressure than the other one, more control than the other one, because you have influenced it by giving something. That type of study is called experimental design. It may be something physical, it may be food. You even say, go and do exercise. You prescribe exercise, weight, all those diet for people for their weight, and later you say you are measuring their height and weight. So, or you prescribe imatinib to some people and diet to some people. Later you say you are taking blood for hemoglobin concentration. You somehow you have influenced what you are studying. That is experimental design. But anytime you are not influencing what you want to measure, but you just go and measure what you want to measure. That is observational. So the people that were doing experimental design, they use the word dependent and independent. The reason being that there are two variables now. You give health education is a variable. Either you receive yes or no. Then knowledge of contraceptive is a variable, whether good or poor. So which one come first? Which one determine which? Which one depend on the other? So the variable health education, yes or no, and variable knowledge of contraceptive. Which one? Both of them are two variable now. Which one determine which?
Health
Which one?
education.
Education.
Health education.
will determine the other
Health
one.
education.
So is the exposure, is that not so? Is the exposure now? Now, which one depend on the other?
The knowledge
The knowledge of
Thank you.
contraceptive
So
depends
now,
on the health
thank
education.
you. So the experimental researcher, that exposure, they now call it dependent variable. That one that is the one that is the first independent variable. Now, so that in that outcome, that one that is being caused, that knowledge is dependent variable. While the other one that is causing it is the independent variable. So in the experimental researcher, we call what is given to influence something as independent variable. What is influencing, we call it dependent variable. But if you now marry together, it means the same thing. What he call independent variable is exposure. What he call dependent variable is the outcome. Can you see now? So it's the same thing. So exposure variable is called independent variable. The outcome variable is called dependent variable. So you can either call it exposure, outcome, independent variable, dependent variable. Means the same thing. Now, the word exposure now, there are many names they call it. Factors.
Sorry, sir.
This where we heard of risk factors. Factors. No, predictors. Those are different
Sorry,
names
sir.
for
Excuse me, sir.
what is it? Yes.
Sorry, I wanted to make sure that I understand the summary of what you just said. The
Yes.
exposure, therefore, is the independent variable, while the outcome is the dependent variable.
Exactly. Yes.
Okay. All right. Thank you.
Yeah. Now, so when you are now stating your hypothesis, when you want to use the word different instead of using association, because if you just use the word there's an association or there's no association or there's an association between this variable and this variable, it doesn't really matter which one you may mention first. It's smooth, it's easy. But when you use the word different, it's the difference in the outcome variable in between the different category of exposure variable. Does it make sense now? So, for example, now salt intake and blood pressure, I will now say that there's no difference in the blood pressure between the people that take high salt or low salt, much salt or not much salt. There's no difference in the teenage pregnancy between the high and low socioeconomic group. or there's a difference between the level of knowledge between those people that receive education and people that didn't receive education. Can you see now? The difference is about the outcome. The difference in the outcome between the different categories formed by the exposure. Does it make sense now? So that is why you can say, when you say
Sir,
there's,
can you just explain it again?
get me, okay? There's an association between salt intake and blood pressure. But you cannot say there's a difference between salt intake and blood pressure. It doesn't make sense. If I want to use the word different, I will not say there's a difference in the blood pressure between people that take much salt and people that don't take much salt. Does it make sense now? So when you are using the word association, you don't need to separate, you don't need to care about which one is exposure, which one is outcome, which one is dependent, which one is independent. No, you don't need to. But when you are using the word difference, you must take cognizance that the difference is about the outcome, which is the dependent variable. You understand? There's a difference in this blood pressure between people that take much salt and people that take less salt. You cannot say there's a difference in the blood salt intake between people with high blood pressure and low blood, because the high blood pressure is the outcome. The difference you are looking at is about the outcome or the dependent variable. Does it make sense now? Okay, leave that one. Now, if you cannot grab everything, when you are doing your, I hope you'll be able to understand when you are doing your research methodology. Now, we have not finished. When we now in hypothesis testing now, whether you say there's an association or there's a difference, whether you use it, that is what we call research hypothesis. Research hypothesis. When you say there's an association or there's a difference between, that is research, and that is because that's what the researcher want to test. But as statistician, you cannot test that, and you are the one that will test. The test hypothesis is statistician that will do it for the researcher. But the statistician cannot test that hypothesis like that. For example, if you say there's a difference between my age and your age, what is the question? You say, what is the difference? So my age may be different from your age by 1 year, by 2 years, by 3 years, by 4 years, by 5 years, by 6 years, by 10 years, by 6 months, by an infinite number of ways. My age will be different from yours. So if you have to test, oh, is it different by 1? Is it different by 1.5? Is it different by 3 months? You have to test. So if there are infinite number of ways, my age will be different from your age, you need to do infinite number of tests. Does it make sense now? But if you now see there is no difference in my age and your age, so there is no difference, there's nothing, it's the same. It means the same. If you say there's no difference, it's the same way as you say there's no association. There's no association between salt intake and blood pressure. No association. It is the same thing. There's no difference in the blood pressure for the people that take more salt and people that don't take more salt. It means the same thing. So when you say there's no, we call it non-hypothesis. That is called what we call statistical. That non-hypothesis is what we call statistic, because that's what the statistician will test. Non-hypothesis, there's no difference, there's no association. Statistical hypothesis. Of course, if there's no true that there's no difference, the alternative hypothesis that say there's the difference will not be true. But if the no difference is not true, the alternative. So that's why they are two mutually exclusive hypotheses. Non-hypothesis and alternative hypothesis. The alternative hypothesis is the one that says there's a difference or there's an association, which is this research hypothesis. The null hypothesis is the one that says there's no difference or there's no association, which is the statistical hypothesis. And the one that is tested with statistics is the statistical hypothesis. Does it make sense? So we proceed. So when you are stating it, many people will state both null hypothesis and statistical hypothesis and research hypothesis. They state the null hypothesis and alternative hypothesis, or we call it statistical hypothesis and what do I call it? And research hypothesis. But stating this, it shows that the person is amateur, it's amateurish stating it. But sometimes many researchers, many examiners want to where is it? Put it there. Because it's a waste of how can you say there's no association, there's association. What I say? Rubbish. Say in a different way. But the logic behind it is the null hypothesis that it will test to show if this one is correct or not. Of course, if you say it's either A or B, you say that I took it is there, it is not there. If you find out that it is not there, is false. That shows that it's there. If you find out that it is not there, it's true. That shows that it is not there. So that's just it. Let's look at the way it works statistically. When you carry out your test, when you carry out your research, two things will happen. Okay, before those two things happen, when you state your null hypothesis, there are two things, two options, alternative options. Even for the null hypothesis, when you say there's no association or no difference, they use the word different, no difference. It may be true that there's no difference. It may be false that there's difference. Null hypothesis, if it is true, that shows that there's no difference. If null hypothesis is false, that shows that there's difference. You state your null hypothesis, there's no difference. In real life, which only God knows, the null hypothesis may be true that there's no difference. It may be false. It means that there's a difference. Those are the two possible options for null hypothesis, as you have stated. When you now carry out your own research study, some of you may tell lies, a lot of crooked things. But whether you do it very well or you don't do it very well, let's say you have done it very well. You say within the limit of experimental error. Now, you may conclude that, you may say that no difference. You find out that there's no difference. If you find out that there's no difference, they say that, okay, you may find out that there's a difference. If you find out that there's a difference, what will you do? You reject no hypothesis that says there's no difference. So if you find out that there's a difference, you reject no hypothesis. But if you find out that there's no difference, you fail to reject it. You fail to reject. So he say you should not accept it. You see, you accept it. You know why you cannot accept it? Because for the fact that you didn't find that different does not mean that it doesn't exist. It's just like somebody said that they said that no man can do that thing. They say no man can unfold this thing, can solve this riddle. And you try. You say you cannot solve it. And I say, no, there's no man. Actually, there's no man. Who are you? It's because you cannot solve it. Another man can come and solve it. Of course, if you solve it, by the time you just solve it, that shows that it is not true that no man can solve it. Because one person has solved it. But if you don't solve it, does it mean that no man can solve it? No, it doesn't mean that no man can solve it. It's because you as a person has not solved it. Another man can come and solve it. So if you know, you find no difference, does not mean that there is no difference. You say you fail to reject. You don't say you accept. You fail to reject it. Does it make sense now? That's it. So that's not where you are going. So I've already said that null hypothesis will give you two possible options. If null hypothesis is true, that should there is no difference. Null hypothesis, if it is false, that means that there's difference. If in real life there's difference, null hypothesis is false. If in real life there's no difference, null hypothesis is true. Only God does one. But you now come with your jamboree work. You also have two options. You either say, I find it different, I reject, or no different, you fail to reject. So if you combine the two, that's why we put in a 2x2 table like this. It gives you 4 possible options. Those two scenarios now create 4 possible mutually exclusive things that can happen. And only one of them can happen per time. And 2 of them are concordant, 2 are discordant. When you say concordant, you can tell me, okay, don't let me waste time asking you that. Which one is concordant? Let's just, you see, the first one I want us to look at is, if, to be sincere, there is no difference. The way no hypothesis is false, is true, because no hypothesis say there's no difference. And if actually in real life there's no difference, and no hypothesis is true, and you do your study also, you find that there's no difference. You know, your decision is correct. Is that not so? It's correct. That's why you see it's correct. Yes, because you find out, you see, you fail to reject, no different. And in real life, no hypothesis true that there's no difference. That's one option. The other correct option is no hypothesis. You find out that there's a difference, and the no hypothesis is false. There's a difference also in real life. There's a difference. No hypothesis is false, and you also, you see, there's a difference. You reject no hypothesis. You are correct. That is the power of the study. The power of the study is ability of the study to find the difference if it is there. Can you see now? The ability of the study to find the difference if it is there. And that is it. Power of the study. Now, we still come back there. So you can now see now, in the real life, there's a difference. In your study, there's a difference. You got it now. That's the power of that study, that the thing is there, you got it. You know, the other one that the thing is there, you say it's not there. Yes, we know that it's correct there. There's no power there. There's nothing there. You see, there's nothing. But this one, there's something, you found it. Now, those are the 2 correct options. But other, yes.
Okay, so in order for you to be sure whether you have made a type 1 or a type 2 error.
I've not reached type 1 and type 2 error. Now, why you ask a question? I thought you want to ask a question about these 2 things I just talked about. I want to talk about type 1 and type 2 error. Why are you asking me a question about that? You asked me talk
no,
before I thought you wanted to ask me a question about the one I've talked.
Yes,
so,
it's still related to the one that you're saying.
It's not related. If it's related, you cannot be asking me type 2 error, because I want to speak about that type 2 error now. Unless you want to ask something about that power.
Yes, I want to ask about whether it is correct and the power. If you are doing a study, and you have got you now decide based on your results whether it is, how do you know whether it is correct or not if you don't know the actual truth from the population? That's the reason why you're doing the research in the first place.
You know,
I don't know if.
Don't worry. All these things, let me tell you something. The power of the study if let's say, well, when you are doing your, so that we don't go into research method, we have already said that the epidemiology is the study. All the research you are doing is epidemiological study. It's epidemiology practical. Yeah, we have already told you public health, the backbone of public health is epidemiology. And the research you are doing is epidemiology research. It's like you are practicalizing epidemiology in your research. And the quantitative foundation is about statistics. The epidemiology depends solely on statistics. You get the picture now. So I don't want us to go too much into the research method because it's somebody's work. But I just want you to understand the statistical basis here. Now, the power you are talking about. So when I teach research method, I actually tell people about that power, I ask them, is power, does the sample size, does he determine the power or the power determining the sample size? It's both of them. The power of the study. Is it before you do the study you know the power, or is the study after the study that you know the power? It's both sides, because you will have determined the power from the inception when you are calculating the sample size. So the sample size depends on the power, and the power also depends on the sample size. Can you see now? So these issues, they are just concepts you need to understand. Once you understand everything, it's just like the way I explained the, what do I call it, standard error. You, at the end of the day, when you say inferential statistics, when you understand, by the time we finish now, you now know, okay, these are the things they are talking about. It's just to have a clue about the population. In some of those things, when you understand it, when you now see the way it is, you're able to know, oh, this thing has power. So you will not be able to get answer to all your concerns. That's why you are jumping the gun. And that's why you are talking about two error. I know where you are going. Let me explain first. When I explain all these things, this question you are talking about, answer to it. Now, let me explain. I've explained the correct option, correct, power. Let's look at this order. They are the disorder. There are two errors that can happen. One of them is this first one. You may reject, you may find a difference. You say you reject no hypothesis. And in real life, it is true that no hypothesis is true, that there's no difference. But you find a difference. You are committed error. Call it error. It's like an error of commission. Something is not there, you say it's there. Type 1 error. Rejecting non-hypothesis when it is true. Look at it. Rejecting horizontally. Rejecting under reject, different. Vertically, non-hypothesis is true. No different. You find a difference in real life, there's no difference. You have rejected non-hypothesis when non-hypothesis is true. There's no difference. That's type 1 error. Now, the other error that can happen is when there's a difference in real life, you find no difference. Okay? Your study, you didn't see anything, you fail to reject. Not rejecting non-hypothesis when it is false. Non-hypothesis is false because non-hypothesis is there's no difference. But for us, there's a difference. But you say, there's no difference also. The whereas is some. So in that situation, you have committed type 2 error. Non rejecting. So some people use the mnemonic to remember. Reject, true. Not rejecting, false. Not false. Rejecting, true. Type 1 error. Not rejecting, false. Rejecting, true, means rejecting non-hypothesis when it is true. Type 1 error. Not rejecting, false, means not rejecting non-hypothesis when it is false. Does it make sense? Now, let me come and explain something around the question you have. if they are to tabulate this type 2 error beta plus power now, if we are tabulating, we say 100%. If we put percentage here, everything to total should be 100%. Power and type 2 error, they are complementary in the sense that if the power is, they add up to 100% or 1. If the power is 80, the probability of committing type 2 error is 20%. If the power is 80, the probability of committing type 2 error. So that thing you are talking about now is when you are now, that is why when you are calculating your sample size, is from the inception. You factor in the samples because it's the sample size that will increase your power. No, we have already talked about it the other time when we talk about sampling standard error. I said that for your estimate to be close to the parameter, your standard error will be small. And what will make your standard error small is when you increase your sample size. No, the sample size was a denominator by that time. When you increase, jack up your sample size, your standard error will be small. Your power will go up. So because why I'm saying that is that it's not all the study you do that the power element appear visible in the calculation. If you are not doing anything that has to do with hypothesis testing, what do I call it? Analytical study, power factor will not come into some sample size. But the power is still there somehow. But when you are doing something that has to do with the two, you have at least two groups, power will come in here. And that beta, this power factor and this one, they will come in. The power, if your power is 80, if you set your power to be 80, your type 2 error rate will be 20. If you want to reduce your type 2 error rate, you increase your power to 90. That one will. But somehow also, if you reduce your type 2 error rate too much, your type 1 error rate will increase. They increase also. So you have to strike balance. Now, we are talking about type 1 power and type 2 error now, how they are related. Let's now talk about this type 1 error. That's the way we are going. That's the most important aspect of it, type 1 error. This type 1 error is the probability of committing type 1 error is the p-value you have been hearing of, p-value. P is probability. P. So p-value you have been hearing of is probability. It's probability just is called. So probability of committing type 1 error is p-value. I don't know because I wanted to draw something. Okay, let's now ask a question. Let me ask a question. If the probability is on a scale of 1 to, say, 0 to 1, if the probability of committing type 1 error mean that thing is not, there's no difference, you say there's a difference. And that's what it means. You reject no hypothesis. You say there's a difference, whereas there's no difference. So something that is not there, you say there. Association that is not there, you say it's there. There's association between salt intake and blood pressure. There's association. You'll be taking more salt too, whereas there's nothing. Your probability of committing of making that mistake and say there's something association when there's no association is p-value. So I want to ask a question. If the p-value is 1, what does that mean? So you unmute and answer me now. If the p-value is now 1, what does that mean to type 1 error? The probability of community type 1 error is p-value. If p-value is 1, what does it mean? Because we are
It's a
talking about
type 1 error.
probability.
Yes.
There's a type 1 error.
That is certain 100% you have committed type 1 error. That's what it means. One certainty that nothing there you said is there. That's what it means. But if it is 0, what does it mean?
You are correct. That's no type 1 error.
That is, you have not committed type 1 error. That is, you have not said something that is not there is there. You have not said something is there when it is not there. That's what it means. But in real life, it's not always like that. Yeah, it can be 1, it can be 0, but it's rare. Most of the time, it will be a value in between 0 and 1. It's just like exam. There's 100%. Yes, people can score 0, people can score 100%. But it's rare for somebody to score in most exams. When it is real exam, not a year exam. Real exam. Rare for somebody 100 is rare, but people can score 100. But it's rare. But it's also rare for you to just score 0. And then the person is dumb. They didn't write anything. But in real life, people will score in between 0 and 100%. Of course, now, if somebody scores 0, you won't be asking if he passed. So the person that scores 0, did he pass? Answer me now. Okay, the person that scored on
No.
No, sir.
No, sir.
The person that scored 100%, did he fail?
Sir.
No,
No.
sir.
No.
It's certain that he passed. He didn't fail. The other one is certain that you're like somebody that scored 0 out of 400 in JAMB. He said that so score 0, I'm looking for admission. That's madness. So somebody's child scores 0 in JAMB, is looking for admission. Whereas, of course, if someone scores 400, imagine someone scores 400 in JAMB, unless the person does not want to do any course, unless he doesn't want to go to school, he will get admission. At least. So, but it's rare. Those 2 occasions are rare. So, in between, there will be some, at what level now will our P value be? For us to say, okay, we want to take it that, we reject no hypothesis and say, yes, there's a difference. So, intelligent people over the year ruminated. They came with an idea. Somebody came with another. Okay, if the probability of committing type, so another way of saying that probability of committing type 1 error is the probability that the difference I've observed is due to chance. But over the years, people find it difficult to understand. But people find easy to understand the way I've explained it now. They mean the same thing. Because, before you do your inferential statistic, you might have done your descriptive statistic where you have said, okay, this thing I'm new, the people that take the high salt, this is their average blood pressure. The people that don't take much salt, this is their average blood. You can see the difference in their average blood pressure. This one that take much salt, they say the average blood pressure is 130. While the people that don't take much pressure, the average blood pressure is 100. See the difference. Average 130, average 100. Then we still want to say this average 130, average 100. We have observed difference now. We can see what we are observing. But that observed difference, is it due to chance, or is it just upon like that, or is it really different? That's what you are testing. The probability that this difference I'm observing is due to chance is the p-value. Can you see now? It's the same thing as probability of committing type 1 error. Is the p-value. Because if the probability that what I'm observing is just a chance occurrence, so if it's too high like that, that is certain that is not a real difference. It's just occurred by chance. So if we do this research again, It may not give us the same thing. It gives us different things. Just a chance occurrence. But if the probability that it's not a chance occurrence, this is very small. There is a chance occurrence. That's what that difference is a real difference. Does it make sense? So the intelligent people now say, okay, 1 out of 20 is an arbitrary. If 1 out of 20 times, 1 over 20 is 1 out of 20 is 0.05, which is 5%. So they now put this thing here, 5%. This 5% now is 0.05. 0.05 from 0 to 0.5. If the probability p-value is less than or equal to this value, we want to assume that no, we have not committed type 1 error. Yes, we have not committed type 1 error. That no, we have not said something is there when it is not there. We have not committed type 1. If it's less than, but if anything greater than this, the probability, that's the essence. It's an arbitrary level. But some people use, on few occasions, use 0.01. That one is very stringent. It's too stringent. People don't use, but most of the time it's 0.05. People use. Are we together now? So this 0.05 is what we call significant level. The probability of committing type 1 error is p-value, or the probability that the difference due to chance is p-value. At what p-value level will you reject null hypothesis is the level of significance. Just like when you say this is the score in school, p-value. The pass mark is this, cutoff point is this. The cutoff point is 0.05, which is the level of significance. So your level of significance. So when you are doing your study now, you have to set your level of significance even from day one, before you can, because during your calculation of sample size, it will be there. The level, we'll talk about it later. The level of, as we are going to confidence interval, the level of significance and the level of confidence, they end up 100%. Just like the way power and type 2 error end up to 100%. This type 1 error and confidence level end up to 100 also. So if your level of confidence is 95, your level of significance will be 0.0. If your level of confidence is 99, very high, your level of significance will be 0.01. That's very, very stringent. Does it make sense? Any question before we proceed? So in hypothesis test, this is the conclusion. So whether you are doing t-test, chi-square, ANOVA, think of any hypothesis test, it ends up with p-value. This value, p-value. Any question? No question. Is it that people are cooking? So I think some of those things are said. P-value is, yes, probably, yes. P-value is probability of making type 1 error and rejecting null hypothesis when it is true. In other words, it is probably that difference due to chance. The significant level is the maximum level of risk that we are willing to accept at the price of our inference from the sample. Well, I don't want to be rating, because if I do break it down to you, it will just be. So if the p-value is less than or equal to 0.05, it means that we have a 5% chance of being incorrect in rejecting null hypothesis or having type 1. So we believe that 5% chance is negligible. But anything greater than that. So if p-value is less than this, we do not have enough evidence to reject null hypothesis or to accept alternative hypothesis. Now, there are some questions that actually come. There are some things. Now, this p-value 0.05, is it this level of significance? Now, is it including 0.05 or less than 0.05? When will you reject non-hypothesis? When will you say something is statistically significant? Is it when it's less than 0.05? When it is less than or equal to 0.05? It has been many statisticians, they have been, some people say less than 0.05. Some people say less than or equal to 0.05. But I'm of the camp that say it's less than or equal to, because the level of significance and the confidence level, they add up to 100. But because you cannot tell me now, when they say at 95% confident, so 95% confidence level corresponds with 0.05, which is 5% level of significance. Unless you want to say at greater than 95%, and nobody say that, it's 95%. Not because if you want to say that until it is less than 0.05, that's your until the confidence level is greater than 95. If the confidence level is at 95, then this level of significance will be 5%, at the 5%, because they add up to 100. That is why I joined the group. Any question? Want to go to the last confidence interval? We are just finished talking about hypothesis testing now. So can you see the way when you reject no hypothesis, that shows that you have accepted alternative hypothesis. When you reject no hypothesis now, that shows that no hypothesis is not true. It's alternative hypothesis that is now true. There's an association between salt intake and blood pressure. Can you see now? So you use statistical hypothesis, which is not hypothesis. By testing it, you're able to help the researcher test his or her research hypothesis. Because you cannot use the research hypothesis does not have that temerity to help you get what you want. So you have to now use your own non-hypothesis as a statistician to test. Then whatever you get, so you now transfer it to the researcher. So that's okay. Your research hypothesis is true. It's correct. If it's not correct, it will tell you. Any question on this? Okay, there's no question. Let's talk about confidence interval. This is a very interesting aspect of statistics, confidence interval. So I've told you it's an inferential method also. Now, for us to talk about confidence, the first thing we want to talk about is, let's look at the word point estimate and interval estimate. Now, confidence level, confidence interval of the mean. Let's look at all this together. What is point estimate, interval estimate? It's very simple. We have already discussed that whatever you get from your sample statistic is an estimate of the population parameter. It's an estimate. It's not the real value, it's an estimate. You are just trying to estimate it. So when you are giving, you calculate the mean percentage. One value like this is a point estimate. One value is a point estimate. But when you give a range of values, it's interval estimate. Let me tell you the logic behind this interval estimate. If I say, okay, one of you now, is it Amanda? I want to get the age of Amanda. And I say, if Amanda is 35 years old, and I want to get the way I'm looking at you to be around between 33 and 30. If I just get, I just want to get, okay, you're 32. You know I've missed it. I just say, but 36, I've missed it. If I say they are between 32 and 37, I'm able to capture the value, even though I'm not sure, because I wasn't sure. That's why I don't want to give a value. I miss. I say it should be between 33 and 36. Now I'm looking at it. I say you are right. You are right. Yes, still, I'm not giving you the, but at least you are right. You guess right. But if I say you be between 30 and 40, you know that I will likely even get it more, because I've given a wider range to capture the age. So because we know that when you take sample, whatever you get can never be equal to what the parameter will be. What if you have taken the whole population and get it? So the estimate can never, whatever you get, it's an estimate. So to be able to improve on your estimate, estimating, that is having a clue about the value of parameter. So you give interval estimate. You give a range of value within which you can say, oh, the values in between. But this range of value also comes with confidence. Just like I have given two scenarios now, where I gave one range short, one range higher. That short range may miss it. If I have already said, if it's 35, another, it should be between 32 and 34. You know, I miss it. I give a range because it's short. If I say between 32 and 36, you know, I've gotten it. So give me a wider range, you will likely capture it. Yeah. And that wider range will give you higher level of confidence than the shorter range. It's the same thing. So, and whether shorter or wider range is better than point estimate. So can you see the logic between point estimate and interval estimate? These estimates, they are so the confidence interval now is a range of value within which you are to certain percent confident you find the population value. So the logic behind is that when you calculate the mean, you also calculate the confidence interval. This mean I've calculated for the sample. But I want to give a clue about what the value will be in the population. I will now give a range of value. I will now say I'm 95% because the level of confidence we usually use 95. You can use 99, but nobody will want anything less than 90. So I'm 95% confident that the population value, the parameter will be in between these two values. Of course, the range of value you give, you're going to see that the lower value will be less than your estimate. The upper value will be higher than your estimate. It's a range of value so that it can give a clue about with a certain level of confidence. And that certain level of confidence, probability C, 95%. That's 95% sure that the real population value is in between these two. That's confidence. And you can calculate for mean, for proportion, for rate, for anything. You can even calculate for difference in mean. Different. In a situation where you are studying two groups, two population, you know, the example we gave, you calculate the mean blood pressure for this population is 130, the mean for the other is 120. You can see the difference of 10. So you can calculate the confidence level of the difference. That difference of 10, you may say that, okay, for this study we have done, we have gotten the difference of 10 in between these two populations. Then that's from the sample, those samples. But in the population, the difference will be a range between this and this. So you can calculate confidence interval of the difference. And this was just to explain what I just said now, the estimate parameter and the estimated one. For continuous variable, they are continuous variable. What do you use for continuous variable? You use the estimate you use for the mean is mean. If you are dealing with one sample, it's mean. If it is two samples, you say different in the mean. Two dependent mean different. So if you are dealing with categorical variable, proportion, rate, all this prevalent, incident, different in proportion, different risk ratio, all those things are related to categorical variable. See, some of these estimators, you just want to decorate this thing here, because we have already talked about it before. By X is the one that is mu, is the one that is estimating mu. Mu is the population parameter, mean in the population, the mean in the sample by X. Standard deviation, this variance anyway, it's variance that is square of standard deviation. That's all. Just to point estimate, interval estimate, just to be. Now, the way it's being calculated, point estimate, what you calculated in your sample. The lower, your interval will be lower limit of the upper limit. You see that the point estimate, the lower, the confidence interval you want to give, the lower value will be less than your point estimate. The higher value will be, interval will be higher than the point estimate. That's why you are still going to calculate your confidence interval from your point estimate. So this one is just giving you the picture, what I'll be talking about. But let me go to, okay, how do you compute it? Point estimate plus your point estimate, either mean or whatever, plus or minus z score. That's z. Who can tell me the value of this c at 95% confidence level? What is the value? I want smart person to tell me. Nobody? All of you
It's
are.
right there.
Say it now. What's the value of z?
1.96.
I say at 95% confidence level, what is z?
1.96.
1.96.
1.96.
1.96.
Which 1.96? Yes, 1.96. All these things, we remember when we're discussing normal distribution, probability and normalization. When I told you now, we say in between -2 and -1, 95.45%. But the researchers are interested in the middle 95%. And now we knew that translate to the z-score 1.96. You just learn to forget. That is the Z. That's z-score. I will calculate that. Instead of the z-score they used to construct standard normal distribution. I say, instead of you talking about the weight of the person, you talking about any value, you change it, you convert it to z-score. And that's z-score. If you are not talking of 95, the middle 95 is 1.96. This value minus plus 1.96. Can you see? So what should now the point estimate plus or minus 1.96 multiplied by standard error. Can you see now? In your point estimate, you have to calculate the standard error of that point estimate also. When you calculate the standard point estimate, you multiply it by 1.96. You remove the value from the point estimate. It gives you the lower limit. You add the value to the point estimate. It gives you the upper limit. The people that did this in their human being like us that just think very well. Think deep. They think deep, come up with this. This one, just to remind you of what I've shown you before. The origin of that. Look at it. Middle 95 minus 1.96 plus 1.96. So confidence interval. Point estimate, reliability factor. That reliability factor is Z as standard error. So you minus it, you add it here. That's how to calculate it. So like for 95, 1.96. If you are dealing with 90, nobody use that 1.64. If you are using 99, that's 2 point. Nobody. So the one we usually use 95%. Now confidence interval. This confidence interval we are talking about. This example, if we were to take 100 different samples and compute a 95% confidence interval for each sample. Then approximately 95 of the 100 confidence level will contain true value. Do you get the statement now? Imagine you you take your sample, you estimate something, you now calculate the confidence interval. You take it 100 times. The approximately 95 of the 100 confidence interval will contain the true value. That is, if you are taking sample 100, calculate the confidence. So your out of 95 of those samples will contain the true population value. That is, you are 100%, you are 95% sure. You are not 100% sure. You are 95% sure that yes, the population value. Who is laughing? Who is laughing there? This person, who is this? Oh? If you are tired of this, something you will leave. Now, there is small assignment for you before we leave. All those ones, don't let me even bother you with. Confidence of means. Though you don't need to bother yourself or how to calculate them. Well, I will not ask you. All this one is just for you, go into deep, just for you to understand the concept. I will not ask you to, but you must understand it, because even when we teach you how to use software to run, if you do understand the logic behind this thing, everything be like magic. It's not what you know. It's not, computer does not do things for you. It's garbage in, garbage out. You want. You manipulate. You use the computer to do what you want. So the confidence interval of proportion. You know, we say you can calculate confidence interval of anything. So this is where I want to ask question. Now, this graph we are seeing is representation of confidence interval and confidence level limit for diastolic blood pressure. The diastolic blood pressure, the population mean is the line you see, horizontal line. The mean diastolic blood pressure is along the horizontal line. You know that vertical axis is the diastolic blood pressure. The horizontal now is if you come 0 to 3, those are the sample, number of samples now. Now, that top, the middle line, horizontal, that is the mean. So there are 6 samples that be taken. You can see their mean and standard deviation. They are represented on the graph also. The mean and the confidence interval, both upper and lower. By the mean itself, which is the estimate, the confidence interval. I want to ask you, how many of them include population mean? How many of them? How many of them capture? How many of the 6 capture population mean? The population, the parameter, capture the parameter.
4.
4.
4. 4. Yeah, you're right. So, any objection? If you don't understand why it is 4, let us know so that before we proceed, before we close.
I don't understand, sir.
I don't understand.
Okay, the people that understand, explain. The people that understand, you should explain. And the people that say 4 is correct, explain.
Amanda, please explain.
Is it Amanda that said 4?
Look at that explaining everything.
Who said?
I said 4.
Celebrity chef. Celebrity chef. Is it you that say Amanda should explain?
Yes, sir.
Okay, you didn't
She
understand.
said
You didn't
she said
understand.
4. I don't understand. She said 4.
Okay. Now, it's very simple now. Look at the first one. You will see that the only 4 cross the horizontal line. That's all. That's all. We have already said the mean in the population, that is the parameter, is that horizontal line. So those 6 sample now, only 4 cross the horizontal line. If you look at the first one, the mean is X here, the lower value, the parameter, the estimate is in the middle and the lower and upper. But this first one, the range does not include the population mean. The number 4 also, look at it, is above. Everything is above the population mean. The number 1, everything is below the population mean. It's only number 2, 3, 5, and 6. Can you see? Those are the ones that their range, somehow, they include the population. They cross that horizontal line. Is it clear now? Is it clear?
Yes, sir.
Okay. Yes, sir. Now, the last thing we want to discuss before we leave, or second to the last thing before we close, is things, sometimes people find it difficult to conceptualize p-value. After they now understand it, somebody will now say that it's useless. Because if you want to publish in Lancet, they tell you that p-value has no place in medicine. Though most of you are not even doctors anyway. The doctors here, we understand what I'm saying. They say p-value has no place in medicine. They say it started with agricultural research in early 90s, when they just dichotomized study into significant and not significant. That's what we are still experiencing now. They statistically significant, not significant. That's all. They say it has no place in medicine. So, if you want to publish in all those high impact medical journals, they want you to come with confidence interval. So I want to tell you why confidence interval is better, superior to p-value. In another way of telling you that confidence interval is superior to hypothesis testing. That's what they are telling you. We talk about these 2 inferential methods. We first of all talk about hypothesis testing, we now talk about confidence interval. So why this confidence interval is superior? There are 3 things you get to know that help you to make conclusion. Out of the 3, p-value supply you 1. Confidence interval supply you all the 3. So there's no point. If that's the case, if what p-value can do for you, confidence interval will do for you, well, bother. But we still use the p-value because if many examiner professionals, they don't understand, they cannot still interpret confidence interval. They don't still understand confidence interval. They still stick to the p-value. But the good thing about it is that the statistics has shown away that if it is correct with confidence interval, it will be correct with p-value. They work together. But the confidence interval supply you more information. That's why when you present your result, some of us, we don't actually need p-value. Don't need to interpret the result. But it's few that can. For most people, most examiner, professional professors, they don't understand how to interpret confidence interval. So what we now do that if we bring the result for people, sometimes we put both there. It's like channel noise, making noise, because too much information that you don't need. Redundant information will be there, but you have to put it for some people to understand. Or else you do good thing, they will fail. Imagine you have done good work. Someone that because of his own stupidity and now fail you and say you are stupid. The stupid person fail the person that have head and say the person is stupid. Because if you fail the exam, you have already told you are stupid. That's what I mean. You say you are foolish. You don't know what you are doing. That's why they fail you. Whereas it's the person that is foolish. But you have to now know how to package yourself. Now, look at what we have on this table. Information provided, there are three. Estimate of the difference. You know, we talk about the estimate. The estimate. Then the second one, whether or not the difference is statistically significant, which is the issue of type 1 error, rejecting type 1 error. The third one is the range of value within which you can find the population parameter. So the p-value only tell you whether or not it's significant, whether you reject null hypothesis or not. That decision to reject, when to reject null hypothesis, that is what p-value tells you. But the confidence interval tells you the same thing. But in addition now, the estimate, the confidence interval will give you the estimate. And now give you a range of value within which you can, to certain percent confident, you find the population value. Does it make sense now? Does it make sense? So the confidence interval give you threefold information, while the p-value give you only one. Now, the relationship between both of them, you have already said it. If it's going to be significant with confidence interval, it will be significant. Because this issue of significance, the only thing that is common to them is this one, whether or not it's significant. So if it's significant with confidence interval, it's significant. Not that you find out, oh, it's significant with confidence interval, it's not significant with if it's going to be, if it's significant with issue, one of them is also significant because they work together. If you look at it, the level of confidence and level of significance, they work together. You remember, we say that they equal to 100%. So now the last thing we now talk about is 2T versus 1T test. So the logic behind when we say 2T, 1T, what does it mean? So when we are trying to do tests to compare two, let's say two population, two group, or two samples now, you know, by the time you do your descriptive statistic, you will see it with your eye that this value is higher in this group than this group. Whether they are all equal, almost the same, or this one is higher than, though the extent to which one is higher may be, really whatever. But the issue that you will see that when I calculate the mean for this group is higher than the mean for this group. When I calculate the percentage for this group is smaller than this one. You will see it. The difference, you will see it. But the essence of average test is that this difference is it by chance or not? So when you are doing the test, if for most of the time the way it is that these two groups, you want to test, you don't want to know which one is higher or not. You don't want to know is there any significant difference. You don't want to know, for example, now you are trying to compare hypertension, the prevalence of hypertension in rural and urban communities. You may have reasons to say hypertension is higher in rural or higher in urban because they are bustling in the urban, whatever. That's not your own. Is you don't want to, you are not testing whether is it higher in urban than rural or higher in rural than urban. Your own is that the difference is statistically significant. It can be higher in any place, but is the difference statistically significant? That is 2T test. But if there are some few situations where it makes only sense, it makes sense only in one direction. You cannot say, I don't want to know, maybe it's higher. You already know This is sacrosanct. This thing is higher in one side than the other, or is lower in this than this one. But we want to see that little that is higher, is this significant? But in the two-tail, it can be higher anywhere. You don't know. You may do your test now. You may discover that hypertension is higher in rural community than urban. You'll be thinking maybe because too much hustling and bustling in urban. So that's why two-tail test, you don't have any preference that one is higher than the other. But in one tail, that one tail test is a rare occasion. It's a rare occasion. I have one example that I usually give, but I forgot. And I fabricated one. I look. What I fabricated is this. Imagine women going for antenatal. And you know that some women, they are still giving birth while their first daughter also is already giving birth. You know, it do happen. So both of them, they can even meet, they go to antenatal clinic together, mother and daughter. So if you have a antenatal clinic where you have some mothers and their first daughters, or even their daughters coming for antenatal, and you are now trying to say, there's no even age difference, much different in their age. So when you calculate the average age of the mother and the first daughter, which one will be higher? This unmute and talk. Which one will be higher?
Mother.
Mother. There's no way the average age of the children, no matter all we just want to know, we know that the average age of the mother is higher. We just want to see that. I didn't even see. Is it different? Is it much? Because most of the time, those mothers also, maybe they marry very early. At the end of the day, now you now see them that there's not even much difference between who they are and their daughter. So in that situation, you know that the age of the mother is higher, averagely will be higher than the machine. But we just want to see that is there much difference? Or maybe that difference is something that is significant. In that case, you are doing one tail test. Because there's nothing like it can be on both sides. The other one cannot be possible. One tail test. So that's the logic between most of our tests are two-tail. And look at the diagram here. It is easily significant with one tail than two-tail. Let me tell you, from this graph, we know why it is easily significant with one tail than two-tail. If you are running a one-tail test, something that wouldn't have been significant with two-tail, it will be significant with one-tail test. Look at this graph now. For the two-tail test, you will see, you remember in 95 in the middle. If the 95, the graph, when you look at the graph, the normal distribution, the middle 95, that's the area in the middle of the graph. The remaining will be 2.5, 2.5 on both sides. Because you know that the Z score, you calculated that time, you start reading it from the middle to the side. So that's why this one will read minus, this one positive, minus side. But if it is one tail, we are reading from the middle also. But because the 95 is on one side, the remaining 5% is one side. It's different from where the 95 is in the middle. The remaining 5% is share 2.5% on both sides. But in this one, the 95 is one side, the remaining 5 is one side. So when you see the area where you are now moving from the middle, this score cannot reach 1.96. It's 1.65. Can you see now? The value is lower than 1.96. That's C score. That's why it is easily. So the other one, they just in opposite direction. It's the same thing, in opposite direction. So, any question? That's the end of the show. Any question?
No, sir.
No question because you want to go. Bye-bye.
No, sir. So some of our brothers and sisters, mostly the Muslims, they want to pray. So some of them
Okay,
wanted
that's
to.
great. Yes, you go and pray, please.
Yeah.
Good night, everyone.
Thank you, sir. Good night, sir. And sir, please, one more thing, yeah. The AOC. Oh, he has gone on.
I'm not gone. I just off that remove. Yes.
Okay. So please, the AOC, you said you were going to.
Oh, which
I
one
don't
is
know if you
AOC?
can.
You are
Area of
seeing.
concentration, some practical questions.
Okay, I will send. Don't worry. I will send it to you in the next 2 weeks. By the time we are
Okay,
approaching.
sir. Okay, sir. No problem, sir. Thank you, sir.
Okay.
All right.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you, sir.